All right, so here we have an induction problem. So we have a 20-turn wire coil in the shape of a rectangle. So this is important, 20 turns. So they give us the dimensions of this rectangle of wire, and we have the resistance. So that we have two positions in the diagram. Position 1, the loop is in a magnetic field which is directed out of the page. And then this magnetic field is 0.2 Tesla. And let's see, it's perpendicular to the plane of the loop. The loop is pulled to the right at a constant velocity, reaching position 2, coming to this position over here in a time of 0.5 seconds, where the magnetic field is equal to 0. All right, so with this info, we want to calculate the average EMF, which is voltage, induced in the 20-turn coil during this period. So to do the first calculation, we're going to use the equation for induced voltage, which is E equals N, which is the number of loops, times the change in flux over the time. Now, I think for this problem, the easiest way to find the change of flux is simply to look at it like this. What is change? Change, so we're going to go N. So what can we write for change? It's simply going to be final. So we're going to go flux final minus flux initial. Change is final minus initial, and then that's going to be over the time. Now, what is the final flux after this loop gets pulled out of region 1? What is the final flux over here? 0. It's 0, because there is no magnetic field. Oh, and I guess I should put down the flux equation. Flux is equal to BA cosine theta. So there's 3 possible ways to change the flux. You could change the magnetic field, you could change the area of the loop, or you could change the angle between the normal line to the loop and the field. Now in this problem here, what's being changed when it comes down to it? Are we changing B, A, or theta? B, because we're going from a region where there is a magnetic field to a region where there is no magnetic field. Long story short, the final magnetic flux is going to be 0, so that reduces our equation to N. And let's not worry about this negative, because in physics, plus and minus is direction. And we're going to figure out the direction from Lenz's law. So just absolute valuing this, it's going to be N multiplied by the initial flux over time. So we plug into this. We have 20 loops. N is 20. The initial flux, we're going to go BA cosine theta. And then the time is 0.5 Tesla. Not Tesla, 0.5 seconds, I mean. So this is going to be 20. The magnetic field is 0.2 Tesla. The area, we got to calculate the area. So we're going to multiply these two dimensions. And the area is, where did I put? 0.0375. So you multiply these two dimensions together, and you get 0.0375 meters squared. Now what about cosine theta? In this situation, what's the angle here? 0. It's 0, because it's the angle between the normal line to the loop and the field. So the normal line is perpendicular to the page, but so is the field, because the field is coming straight out. So cosine of 0 is 1, so we can just leave that out. We'll just put 1 there, and then 0.5 seconds. So this gives us an induced voltage of 0.3 volts. Okay? Now, second question. So everybody got this copied? You got?
Well, you wouldn't give us an angle, would you? We can assume that it's going to be cosine of 0.
Most of the problems, there is no angle. It's just 0 degrees. But I think in the homework set there were problems where there was an angle. Okay, so B. How do we calculate the magnitude of the current induced in the coil? Well, we're just going to use Ohm's Law. The induced voltage equals I times R. So the induced current is going to be the induced voltage over the resistance. So we just found out the induced voltage was 0.3 volts, and we have a resistance. The resistance is given to be 5 ohms. So this gives us 0.06 amps. Now, how do you find the direction of the induced current? To figure out the direction of the induced current, you have to do Lenz's law. So as a result of the loop going from here to here, the first thing is you have to find out which way the flux is changing. Which way is the change in flux? Which way is the magnetic flux in position 1? So dots represent magnetic field coming out of the page. So which way is the flux when the loop is in position 1? Which way is the flux? Out. Dots are out. Dots are out. So the magnetic flux is directed out, and then the loop gets pulled over here to position 2 to where we have 0. There's 0 flux. So which way did it change? If you go from having an outward flux to 0 flux, which way is the change? It's in. It's definitely not out, because what out would be, if the change were out, that would mean that the magnetic field intensity got greater or something. So you can almost think about it like this magnetic field that is directed out of the page died. It went and died to 0. And which way was it dying towards? It was dying into the page. So the change of flux is in. So if the change of flux is in, that means the induced current in this loop, the induced current must make a magnetic field that is out, right? So here's where you use right-hand rule number 2. So if you put yourself like right here on this loop, like right there, you want your 4 fingers curling out of the page when you're on the inside of this loop. So that's going to give us a counterclockwise current. The current must be going counterclockwise, because if the change of flux is in, that means the induced current makes a magnetic field that is out. So you apply right-hand rule number 2 to this loop, and that gives you a counterclockwise current. Okay, part C. So we want to calculate the power dissipated in the 20-turn coil. So here's where we have to use power equations. So power, there's 3 power equations for circuitry. P equals I delta V, P equals I squared R, P equals delta V squared over R. So which one would be the nicest one here? Well, we know what the induced current is. The induced current was found to be 0.06 amps, and then the resistance is 5 ohms. So I would use this one. So we're going to go P equals I squared R. So we have 0.06 amps squared. The resistance is 5 ohms. So this gives us 0.018 watts. Okay, now part D. I want to quickly just review something with you so you're clear on this. Oops. Wrong thing.
Father, we're going to get a question similar to this, right, on the test on Monday?
Well, I'm trying to do 3 problems today, so revert, okay. So it'll be, something, it'll be in this ballpark. Okay, so where are we? Calculate the magnitude of the average force necessary to remove the 20-turn coil from the magnetic field. So here's what I want to review with you. If you have a magnetic field, so let's say you got a magnetic field like, I'm just going to draw in X's. So just follow me for a moment. If you have a magnetic field with a wire in the magnetic field carrying current. So we'll put a little resistor right there. So here we have magnetic field into the page and then current cruising around like this. What we learned with magnetic fields is that current in a wire is simply moving charged particles, right? So you can imagine a positive charge in this wire cruising to the right. Would this magnetic field exert a force on that positive charge which is inside this wire? Yeah. and there's going to be a force on the wire from the magnetic field. So the equation you probably have memorized for magnetic fields, force of a magnetic field equals QVB sine theta, like that. But this equation, when you have force on a wire, when the moving charge particles are in a wire, this equation becomes something different. But it's really the same thing. So let's say that this length of wire right here is L. Just follow me. This is length L, and we have this charge moving through the wire. So Q, now what would the velocity of the charge be? It's going to be this length, so that the charge goes from here to the other side, which is L, over time t. Wouldn't that be velocity? Velocity would be this distance right there divided by the time to get across, and then bring the b down and then the sine theta down. Well, what is Q over t? Q over t happens to be the definition of what? Current. So this is going to be ILB sine theta. So this is the equation that we're going to use in this part of the problem. The ILB, which when I taught it to you, I think I always tell kids just remember Bill, B-I-L. That's the equation for force of a magnetic field on a wire. Okay, now if you think about what's happening here, as this loop gets pulled out of this region of magnetic field, we know that the current is going to be counterclockwise. So I'm going to label the current on here. So current is going around like this. Which way is the force of the magnetic field going to be on this part of the loop, right here? So how do we figure out the direction of the force of the magnetic field? We're going to use right-hand rule number. I'm going to blow this up real big. So looking at this the left side of the loop. If you do right-hand rule number 1, so which way is the current going?
The left.
No. Well, we're focusing on this part of the loop, right? In a minute, we can talk about the top part and the bottom part, but let's talk about this part of the loop right here, this portion of the loop right there. The current is going down. Which way is the magnetic field going? Out. So your 4 fingers are out. The palm of my hand faces to the left. So using right-hand rule number 1, the force of the magnetic field must be to the left. It's got to be that way. Okay? Now, what's happening to the loop? The loop is being pulled to the right. So let's call this the applied force. So if this loop is being pulled out at a constant speed, which I think the problem does say it's moving out at a constant speed, so we sum the forces in the x direction. In the x direction, we have 2 forces. We have this applied force to the right, and we have this force magnetic to the left. So you sum the forces, you go force applied minus the force magnetic. Sum of the forces always equals ma. Well, what's the acceleration of the loop? 0, because it's being pulled out at a constant velocity. So the applied force pulling the loop out of the magnetic field is going to equal the force of the magnetic field. Which, by the way, what is the equation for force magnetic? Well, if it's a current in a wire, what's the equation? I, L, B, and that is QVB, but it's for current in a wire. Did that make any sense?
Yeah.
So force applied, we're going to take the current, which we found out to be what was the current? 0.06. The length, now we want this dimension here. That dimension there, which is going to be 0.15 meters. And then the magnetic field is 0.2. So this gives us an applied force of 0.0018 newtons. But how many loops of wire is this? 20. So this is for one wire. So what you got to do is, since there's 20 loops of wire, you multiply that by 20 to get the total force, which is 0.036 newtons. So that's the force required to pull the loop out. Yeah?
Why isn't it on the right side of the loop? There's also a magnetic force.
Oh, good question. There would be, but I think the idea is pretty much this right side of the loop, as soon as the loop gets pulled slightly, so let's see, which way would the force, there would be a force magnetic there, because the current, let's see, the current is going to be going up, so the current's going to be going up, so do right-hand rule, so the force magnetic is going to be this way, but see, the thing is, they have this set up such that as soon as the loop starts to move, this portion of the loop exits the field, right? Like it's right on the edge. So as soon as the loop gets pulled, you're not going to have this force magnetic acting on that right side of the loop.
And then
Yeah.
the top length and the bottom length cancel each other?
Yes. Okay, so let's talk top and bottom. So which way is the force magnetic on the top? The force magnetic is going to be what? Up. Doing right-hand rule number 1. And then force magnetic here is going to be down. So those forces cancel. So in order to pull the loop out, so like, yeah, this portion right here, the right side of the loop is going to be out of the field pretty much instantly. As soon as it gets tugged to the right, the right side's going to be out, which leaves the left side there. Okay? Okay, part E. All right, identical wire is used to add 20 more turns of wire to the original coil. How does this affect the current in the coil? So let's start with Ohm's Law. E equals IR. So current is going to be induced voltage over resistance. Now, what's going to happen to the induced voltage? If we add 20 more turns, which is basically doubling the number of loops, well, what's our equation for induced voltage? N times change in flux over the time. So what are we doing to this induced voltage? By doubling the number of coils. If we take N and double it, what's going to happen to the induced voltage? It's going to double. The induced voltage is going to double. Well, now wait a second. Resistance. So here's an equation we haven't talked about for a while. If you have a wire, in fact, let me make this wire a little fatter. If you have a wire of, so this represents a wire of cross-sectional area A, length L. If you remember this equation, I'm going to walk to you personally and give you a nice big high five. What's the equation for the resistance of a wire? There's an equation for it. Yes, resistivity L over A, where A is the cross-sectional area. This is for finding the resistance of a wire. So if we add 20 more turns, what are we doing to the length of the wire? We're doubling it. So what did we do to the resistance? It doubled. So we ended up doubling the voltage and therefore and also doubling the resistance. So we have doubling over doubling. So what's going to happen to the induced current? Nothing times 1.